Okay, sorry about that. I accidentally cut off that video. I hate it when that happens, but my finger hit the key and it turned it off. So we're going to finish this, but I'm actually in some ways glad because the turn some more light on. Because there's part that I got so involved in explaining this that I forgot to mention. So let me start with something which is mentioned right at the very beginning. You may ask, why is this the way it is? Why do we end up with tetrahedral? Why does this go to 180? Why when we have a linear molecule, why doesn't it do something like this, where it says, you know what? Rather than this, why not go like that? What's wrong with that? Well, the answer comes from a theory called the VSEPR theory. Actually, it would be this. And that stands for valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory. And what electron pairs, remember electron pairs are any region, lone pair, single bond, double bond, triple bond, any grouping of atoms that are held together around the atom, that those are called valence shell, that's the outer shell, electron pair, they are going to repel each other. Repulsion means to push us far away. If somebody is repellent or repulsive to you, you want to get away from them. So let's say that we have, and I've lost one of the little, well, I can get another one. Let's say that we have these two. This electron, this is an electron pair and this is an electron pair. What valence shell electron pair repulsion theory says is this electron region is going to move to get as far away from the other one as possible. And that would put it right there. We would have our linear molecule. Oh, there we go. Sorry about that. If I have three pairs, and again, three pairs could be a double bond and two single bonds. But if I have all three of these, they're not going to get close to each other. What they're going to do is they're going to move so that they are as far away from each other as they possibly be. And that makes sense why that would be at 120 degrees. And that is predicted by the valence shell electron pair repulsion theory. Well, what about the fourth bond? Why doesn't it go to 90? Well, the reason is that by starting here and coming down not 90, but 109.5 degrees, if that's 90, that's 120, 109.5 is somewhere there. And then coming down from this one, 109.5, and then rotating over from this one, try that again, coming down from here, 109.5, and rotating over from this one, and then doing the same thing, what you'll find is every one of these angles, if I've done that right, is 109.5 degrees. That's as far away as they can get. That is further away than 90 degrees. Now, when we pop this one off, even though there is not an atom there, this stick, representing a pair of electrons, is still a negative region. And I still have four electron pairs. Three that are single bonds in this case, one that's unpaired. What's really interesting is that this one will actually be more concentrated close to the center. If you remember remember when we drew our diagrams? If this is more negative, this electron will be orbiting both parts. There's a negative region in here where the electron is being shared, but it's actually extended out a little ways. Whereas this one, those electrons, you can actually think of them as almost like a single dot right there. And as a result, this will actually push these a little bit closer together. I'm moving, I know it's hard to see, but I'm moving those down a little bit. And all of a sudden, although you have the same basic shape, you have this 107 degrees. Turns out that this is a little more than 107. This is like 111, but the bond between these bonds is 107 degrees, from here to here, from here to here, and from here over. When you go to this one, the bent or the V-shaped molecule, you lose one more of these, and these two will push these two even closer together. Same reasoning. And by the way, this is the water molecule. We call this the Mickey Mouse molecule. And I call it that, and that's what it looks like. And these bonds are 104.5 across. And that's again because both of these pairs of electrons are pushing this closer together. So that's called the VSEPR theory, and it predicts that everything will move as far away as possible. So I was in the process of going through and doing some problems. I'm going to continue that. Problem number 79 and 80 ask about the number. Problem 81 and 82 talk about the VSEPR theory and predict the molecular structure. So for instance, 81A is NCl3. Once again, you have to draw that, and I'm going to do this real quick. You'll have to spend more time with it. And they want you to predict the molecular structure. The molecular structure is this column over here, and in this case, this would be trigonal pyramidal. So 81.8 is trigonal pyramidal. So if they ask for the electron arrangement, they're asking for this column. Trigonal pyramidal is this column. 83 does the same thing, but it uses a polyatomic ion. So for instance, 83A says that we've got SO4 with a -2. So you're going to have to draw I'm going to do this one, S, and we're going to have O, and it's a -2. So oxygen looks like this, and another oxygen here, and oxygen here, and an oxygen here. And then because we have two extra electrons, one can go here, one can go here, and we end up with SO all the way around, and we would write it like this with a -2. But the structure is tetrahedral. I have 4 bonds and no lone pairs. If you go to 85, 85 says for each of the following, indicate the bond angle between them. So now we need to use that bond angle column. And once again, you have to draw your Lewis structure. So 85, let's say we have, well, they have H2O. So H2O is going to be this. But because it fits this category, we would say 109.5. But if you want to make me happy, do it as 104.5 degrees. Your back of your book will say 109.5. And finally, problem 87, predict the geometric structure of the carbonate atom and find the bond angles. So we would need to do carbon, oxygen, and another oxygen, and another oxygen, and we can take 2 electrons and we can move 1 electron in here and 1 electron over here. And so I have 8, 8, but here I have 7, and here I have 7. So we're going to have to make a double bond. And this then, a carbonate is CO with a double bond, a single bond, and another single bond. And we would write it like this, and it would be -2. and that would be this one right here. It would be trigonal pyramidal, and they would say 109.5. But again, I would be really happy if you said 107 degrees. So that is a fairly difficult section, and this long assignment is primarily what we're working on this week. I would normally in class have spent 2 or 3 days with labs where you would have been making these models. We would have used little candies, and you can eat the candies if you want, but you know, there's some things that you can't get when you're here here. There's one more lesson I'm going to do, and that is on polarity. And that will finish up this section on chapter 11. Remember, what we're doing is do the homework and we'll get credit. By the way, I've been keeping track of the homework. I have not entered it yet. I should have that all done by everything that comes in through the weekend. I will have up by tomorrow evening. I've been kind of grading it and holding on to it, and I should have been entering it, but I'll get that done. So we will take our class time and on Wednesday and go through problems with this. And of course, I have my office hours. And as always, you can always contact me. You could even just email me and say, Mr. Bucher, could we set up a time where you and I do a private chat or private WebEx meeting? And I would certainly do that. This concerns me because this can be fairly tricky to nail this down. So I'm going to close there. Like I said, we'll have one more video on polarity, and that will finish up our week. And I don't know if I'll have that up tonight, but it'll be before the end of the week. So, all right, and we'll hopefully see you soon, although I've heard now that the shelter-in-place orders have been extended out to the end of April. So I guess if we do get together, it'll have to be all the way to May. So that's pretty amazing. Anyways, we'll see you later. Bye.